What if the universe isn't sitting in the lowest valley of its possible states? What if it's balanced on a kind of meta-stable ledge, and at any moment the universe could tunnel to a deeper, more comfortable minimum? People hear vacuum decay and imagine Hollywood-style catastrophes, a bubble that expands at light speed like a wrecking ball. That's the misconception. The real story is subtler and stranger. Vacuum decay begins with something tiny, often a microscopic false vacuum bubble seed. Then it triggers a macroscopic rearrangement of energy and entropy. The unsettling question isn't whether it will happen tomorrow. It's how nature can behave, as if it's running a probability distribution over entire realities. And because our best models of the early universe and the Higgs field rely on quantum potentials with multiple valleys, the mechanism of nucleation is not just a speculative plot twist. It's a diagnostic tool for the foundations of cosmology and the possible fate of the vacuum we live in. To understand the before, picture the vacuum not as empty nothing, but as a quantum state of fields. In quantum field theory, fields can sit in different minima of an effective potential, like a landscape drawn by the energy density as a function of field value. A true vacuum is the global minimum, the lowest energy state, stable against small perturbations. A false vacuum is a local minimum, stable for a while, but with a deeper destination. Classically, the field can't roll uphill or tunnel through the barrier without help. Quantum mechanics provides that help through tunneling, but tunneling requires fluctuations to assemble the right configuration. Historically, this idea sharpened in the 1970s with Coleman and collaborators, who developed a Cephalon critical method to compute decay rates of metastable vacua. For a long time, intuition treated the decay as a single dramatic event. Then the picture evolved. Nucleation is a statistical process, and entropy matters, not only the energy barrier. The entropy burst phrase points to a deeper theme. Once the system transitions, the energy budget and degrees of freedom can reorganize explosively, especially in the presence of coupling to other fields and in an expanding universe. Here's the core mechanism. Imagine the false vacuum as a bowl with a lip. The ball, the field configuration, rests in the bowl. Classically, to get to the deeper bowl beyond the lip, it needs to climb over the barrier. Quantumly, it can tunnel, but tunneling doesn't mean the entire universe transforms at once. Instead, the vacuum decays by nucleating a bubble, a finite region where the field value has shifted toward the true vacuum. The nucleated bubble has two competing energies. There is a volume term. Inside the bubble, the energy density is lower, so that region is energetically favored. There is also a surface term between the false and true vacua. The field must change across a boundary, costing gradient energy and creating a wall with tension. More bubbles have too much wall cost. They tend to collapse back. Large bubbles have enough volume gain to win over the wall cost. Once they surpass a critical radius, they grow. Quantum mechanics lets the system fluctuate into a near-critical bubble configuration inside the false vacuum without needing to climb the barrier deterministically. In the theoretical formalism, that fluctuation is encoded in a special Euclidean solution, an instant on that dominates the path integral. The nucleation rate becomes the probability per unit time and volume that such critical bubbles appear. And crucially, this is often exponentially suppressed by the action associated with the instanna. That exponential is why metastable vacua can survive for immense times despite being unstable in principle. After nucleation, the bubble wall accelerates outward. The field inside relaxes toward the true vacuum. For a brief moment, the local energy difference can be converted into motion of the wall and into excitation of other fields, reheating the bubble interior. That's where entropy enters the narrative, not as magic, but as accounting. The false vacuum stored potential energy. The decay products populate many modes, particles, radiation, possibly gravitational degrees of freedom, so the entropy density inside can rise rapidly. In an expanding cosmos, that energy release may also drive local reheating and affect the distribution of matter. The result is not necessarily a literal big blast at light speed through space, but a causal propagation of the bubble expansion governed by the relativistic dynamics of the wall and the space-time geometry. If the decay happens, what starts as one quantum fluctuation can seed a macroscopic domain of a different vacuum state. Now zoom out. Why does this matter beyond answering a curiosity about the universe's fragility? Because our leading pictures of fundamental physics depend on the vacuum structure. The Higgs field, for example, has an effective potential that can admit metastability at high energies depending on the measured top quark mass and Higgs couplings. That means the question, are we in the true vacuum, becomes quantitative. Moreover, in the early universe, inflation itself can be viewed through the lens of vacuum-like energy driving expansion. During inflation, transitions between different vacuum states, if they occur, can generate bubbles, reheating regions, and potentially observable imprints in cosmological perturbations. Even when the decay rate is tiny today, the mechanism constrains models of new physics. If a proposed vacuum would have decayed too quickly in the past, the model is ruled out. Vacuum decay also touches black holes and gravitational effects. Gravity modifies the effective potential and the tunneling geometry, changing both nucleation and growth behavior, which has consequences for the relationship between thermodynamics, entropy, and quantum gravity. That's the entropy burst connection to a bigger picture. Phase transitions are where the abstract math of quantum potentials meets the tangible arrow of time, because entropy production is how energy released by a false vacuum becomes a thermodynamic statement about disorder and accessible microstates. The universe's shape and field space isn't just a static drawing, it's a dynamical process with statistical teeth. So where does this leave us? We started with a misconception. Vacuum decay isn't necessarily an immediate annihilation. It begins with probabilistic nucleation of a critical bubble. We built the mechanism from the landscape of effective potentials: false vacuum metastability, a barrier, a wall cost versus a volume gain, and a quantum fluctuation that forms the right bubble size. Then we followed the consequences. Once the bubble exceeds the critical radius, classical expansion takes over, converting vacuum energy into excitations and driving a surge in entropy through particle production and thermalization. The deepest takeaway is that the vacuum is not passive. It is a state with metastability, and quantum mechanics tells us how rare events in a tiny region can reorganize the global energy configuration of the fields. The universe may be stable most of the time, but stable in quantum physics often means protected by an exponential and not guaranteed by impossibility. If you want more dives into the hidden mechanisms behind reality, subscribe, because the next episode might start with a bubble you can't yet see.